Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, I would like to continue our class on fatigue and fracture mechanics. We're going to cover lecture 9, effects of temperature, loading rate and constraint. So the first thing is we're going to talk about the introduction on the slide, and then the effects of temperature on fracture toughness, and then effects on loading rate on fracture toughness, and the last one is effect of constraint on fracture toughness. Alright, for the introduction, fracture properties of various materials are very sensitive to loading rate and temperature at which the test is conducted. Therefore, K1C value, which is the fracture toughness that are obtained from slow loading under plane strain conditions, are defined by ASTM E399 are not adequate to describe wide spectrum of fracture behavior. Other fracture toughness properties are defined as follows. K1C in bracket T is actually means that the K1C is depends on T, which is K1C is in the function of T, where T is actually the time. The fracture toughness under intermediate load rate conditions where the time to maximum load is given in the parentheses. Okay, K1I, the dynamic crack arrest. Okay, A here is referring to the arrest fracture toughness, while the last one is K1D, the critical plane strain stress intensity factor under conditions of impact loading, which is very rapid motion. K1C in bracket T, which is K1C in the function of time, and K1D tests are frequently conducted at various temperatures to determine the static, intermediate, and dynamic fracture toughness of various structural materials as a function of temperature. The fact that the inherent fracture toughness of most structural steels increases with increasing test temperature is well known. What is not so widely known is the fact that the same inherent fracture toughness can decrease significantly with increasing loading rate. That is, K1D can be smaller than K1C at the same test temperature. Also, testing plates thinner than those required for plane strain values may result in plane stress Kc fracture toughness values that are considerably higher than the K1C values. Okay, thus, before the engineer can use fracture toughness values in design, fracture control, failure analysis, or fitness for service, the critical fracture toughness value for the particular service temperature, loading rate, and constraint level must be known. Okay, let's take a look at this graph. This is actually it is summarizing the effects of temperature and loading rate on K1C, which is a slow band here. K1C T is intermediate, while K1D is the dynamics. So if you see the plot here, it is actually referring to the temperature versus the K1C for several type of condition. Slow band, intermediate, and the dynamics. Both K1C and K1D increase with increasing time temperature. If you see with the time temperature, with the increment of temperature, where it will goes in this direction, you can see the K1C and K1D is actually also increased. Okay, for any given temperature, the fracture toughness measured in an impact test K1D generally is lower than the fracture toughness measured in either of the other two types of tests. Right? For any given temperature means that if I take at the lower temperature, it's always K1C will always the lowest compared to the slow band and intermediate condition. If I take at the higher temperature as well, it will be the lowest as well. Okay, at any this is the effects of loading rate on fracture toughness. At a constant temperature means that I have fixed temperature, for example at a room temperature or any higher temperature, you will see the same trend, but it will be differ in terms of its magnitude. So at a constant temperature means that the test has been conducted at the same temperature for these three tests. Fracture toughness tests conducted at higher loading rates generally result in lower fracture toughness value. Of course, because the dynamic is very fast. So it's mentioned that fracture toughness tests conducted at higher loading rates means that at this value, impact or K1D, is always lower fracture toughness value. You can see this plot at y-axis. It always be the lowest compared to intermediate here and the slower loading rate. So the similarity of K1C and K1D with CVN test Chappie V notch. CVN is the Chappie V notch test. A similar effect of loading rate exists for CVN specimens test in 3-point slow band and standard impact loading. Okay, this is the similarity of K1C and K1D with CVN tests. The general effect of a slow loading rate compared with standard impact loading rates for CVN specimens, where CVN is actually referring to the Chappie V-notch specimen, okay, is to shift the CVN curve to the left and to lower the upper shaft value. Okay, this graph. This is the schematic representation of shift in CVN transition temperature and upper shaft level due to strain rate. If you see here, this is the first plot for the slow band, or I would say this for the K1C, and then this is the impact plot for the impact K1D. At one point, with respect to the temperature, with the increment of temperature, these two plot is coincide at this point, right? If I take one point, which is this is the energy level at which temperature shift is measured. Let's say I would say I want to measure the energy level at this point. So how much is the temperature shift? First, you need to see where is the point that you want to select. Let's say this is the absorbed energy point. So take this point and then you just extend the line here. Okay, now where is the coincidence happen? Where in which this is at this point. So just extend this line. So I will see the point that coincide between these 2 points, and then you just extend this length for the impact towards this point. This is what we say the energy level at which the temperature is measured, and then you will see how much is the temperature shift in transition temperature range measured from here to this point. So that's how we do this approximation. And then for the shift in upper shaft level, I will I will find that from the highest point of the impact loading until at which the the highest point of the slow band. At which temperature? At any temperature. Okay. This is like we said, or we have discussed last time, this the Chappie V notch impact test, where I have this the ready specimen as in here, 55 millimeter, and then the thickness as 10 millimeter, and then I have this length as 10, this width as 10 millimeter as well. Right, the dimension of the CVN test specimen before and after testing, because once you put the load, it will break. So like we have the one that we did last time is the traditional evaluation method of fracture toughness, where we put the specimen here and then I will just drop this and then I would measure how much is the length or the height of the impact of this measurement took place after the impact. So I have H1, this length, the first one, and then how much is the final length. From that, this energy absorbed by the specimen related to the height, this differential H1 minus H2 is recorded on del D. Means that once you release and then it hit the specimen and then it goes up to this point, is everything has been recorded in this features or this screen. Alright, the CVN energy versus temperature behavior of various materials. The same plot like the air temperature and then the Chappie energy or the absorbed energy. Okay, but it will be differ in terms of the different type of various type of material that you apply or you want to calculate. For example, if this is aluminium or aluminium 75, always lowest compared to aluminium 38, and so on. Right? It's just in terms of what type of material that you apply. Okay, the effects of loading rate and temperature on CVN test results. Data for A36 steel. Okay, if you see the same plot as well, but this is for the different in terms of the loading rate, which is the indicator for the square is for the impact, while for the circle is for the slow band, and then you can find what is the different from the point here to here, and then what is the shift temperature based on this plot. So every type of material they have their own plot, but you need to make sure how to find the coincidence point. For example, this is the coincidence point, and then you just need to extend that. Later on, you just need to extend this point as well, and then you find at which absorbed energy that you want to measure until towards this point. Okay. Okay, this is the impact loading rate temperature shift. The shift in the transition temperature for slow band and impact K1C and CVN test results for steels having yield strength in the range 40 to 150 KSI are related to yield strength as shown here. Okay, this is the plot for the yield strength, sigma y, and then this is the shift in transition temperature. So basically from this graph, they put for several specimen and then test that, and then they get the result for the shift in transition temperature. Okay, so from that, they plot the data and then they get the relationship between the yield strength and the shift in transition temperature. In this case, for steel with sigma y between 250 megapascal and 965 megapascal, which is almost about 36 ksi to 40 ksi, they found the relationship, the linear relationship. If you see here, it will be 250 T shift equal to 215 minus 1.5 sigma y. Okay, this is just a mathematical expression for the linear relation that I believe that every one of everyone here have done that in mathematics. Okay, means that if you go or you extend the graph, it will reach the point where it's happened to be 200, 215, and the graph is negative, means that it is inversely proportional. Okay, for steel, means that once you have the relationship for like in this case, you have the relationship like this one. The shape is equal to this relation. Uh, if let's say you want to know at what point the steel exceed uh, the sigma y equal to more than 965 megapascal. So it happened to be 0 at this point, right? T shift will be 0 at this point where you get the length here, the value of sigma y here. Okay, you just need to substitute everything and then you can get what is your value for sigma y. Okay, the intermediate loading rate shift. Strain rates between 10 power of negative 3 per second to 10 per second. Okay, they give us the relationship of T shift, the temperature shift, equal to 150 minus sigma U strength times strain rate, power of 0.17. So they already gave you this equation where you just need to plug in the value for any other material. Okay, means that if I have 130 sigma yield, so this is going to be my plot, or it's going to be 90. So this is my plot, and then I just need to apply how much is the value that I want to check for the strain rate, put it here, and then you get what is your T shift. Other than that, you can just use this graph. Okay, for example, determine the K1D to K1C temperature shift for LBSB steel, where they give you the sigma y, sigma U strength is 40 KSI, and so on. So you have 4 type of material here. Of course, if you have 4 type of material, you will have different sigma yield as well. So you just need to apply the formula, the temperature shift equal to 215 minus 1.5 sigma yield, and then you just check how much is the temperature shift. Alright, the CVN K1D, K1C correlations. The fracture mechanics tests are very complex and expensive. Okay, result of much simpler tests such as CVN impact tests can be used to derive values for fracture toughness. There are procedures to correlate CVN data with KC data. In transition zone, where loading rate is important, CVN can be correlated with K1D. In the upper shelf CVN, the behavior is plastic and the temperature loading rate has little effect. K1C can be directly correlated with CVN. Okay, this is the two-stage CVN K1D and KC correlation. A correlation between CVN and K1D test results have been developed for the transition region. This correlation is given by the equation K1D squared divided by E, where you know that E is the Young modulus of each material, equal to 5 CVN. Okay, K1D in this unit, E is in PSI and CVN is in the feet pound. So K1D can be related to K1C through the temperature shift. In this case, if I know how much is your sigma yield, and then I can check for E. Okay, this is the two-stage CVN 1D KC correlation as well, but this is through the plot of graph. If you see, this is the graph with the increment of temperature. Okay, the trend is not linear, so it will be lower half of the CVN curve with the and it will increase with the increment of temperature. I mean the CVN impact here. Okay, it's going to be lower in this direction, but it's going to be half lower. Means that if this is 4, this is going to be 8, this is going to be 16. Almost like that. Okay, almost linear. Okay, but this is for the K1D. The graph is referring to this plot, and then this is for the K1C intermediate, this plot, and also K1C for the slow bend, this plot, for this plot. So this is the K1C K1 intermediate or K1D plot with the temperature. It's just the same like we have covered just now, but this is more into the formula. You just need to put the formula for this, and then we check for at which level of this graph happen, and how it's going to related to each another throughout this equation. Okay, this is the K1C CVN upper shaft correlation. The graph of CVN plot and then versus K1C for several type of material. So they give you the relationship of this plot throughout this equation. K1C divided by sigma U stress square equal to 5 divided by sigma U stress times CVN that you have calculated towards this equation just now. Okay, this is the CVN, and then minus sigma U stress divided by 20, so that you will get this relation. Okay, now we move into the effect of constraint on fracture toughness. All material outside the immediate crack front region has a simple plane stress state. Okay, outside of the immediate crack front, this is the crack front, so outside of that has a simple plane stress state. Okay, material very near to the crack front. For example, if I take this point, the material very near to the crack front has large plastic strain, and it wants to contract more than surrounding less strained material. Surrounding material constrains the thickness contraction. Okay, if I put if I take or I consider this to be measured, it's going to generate tensile sigma ZZ stresses in this direction, but this must vanish on external free surfaces. Okay, effect of constraint on fracture toughness. For every thick plate, the true thickness stresses at the center line are large, and a triaxial tensile state of stress occurs ahead of the crack. This triaxial state of stress reduces the apparent ductility of the steel by decreasing the stress stresses. You need to mention what is, you need to understand what is triaxial state, means that it's going to be the sigma xx, sigma yy, and sigma vz. Okay, because yielding is restricted, the constraint ahead of the crack is increased, and thus the fracture toughness is reduced. Thus, the fracture toughness is smaller for thick plates compared with compared with thinner plates of the same material. Okay, this is just a conclusion for how if you want to measure for the same material, for the same specimen, but it just differ in terms of thickness. The fracture toughness is always smaller for the thick plates. Okay, due to this reason, this triaxial stress, state of stress, because it has reduced the apparent ductility of the steel. Okay, you will get a different result for different type of material. For in this case, it's just about the steel. Alright, this is the plot for the effect of constraint on fracture toughness. You increase the thickness, you just decrease the fracture toughness. You can see based on trend here. If I take this value for thickness, for example 5, so I have a higher fracture toughness. But if I take maybe here 30 mm or something, it is always lower compared to the other one. Alright, why is that? Because this is in terms of plane stress behavior, while this one is, once you reach this point, it will be plane strain behavior. Okay, means that even at what point you just, once you achieve this point, you may raise or you may increase the thickness as well. The fracture toughness remain the same, or we said the K1C always be constant once you reach this value. Okay, the effect of constraint on fracture toughness. If you see here the stress in structure, I would say that if I have a triaxial direction, sigma 1, sigma 2, and sigma 3. Uniaxial tensile test for the case B, I have max. This is measurement for the shear, and then equal to sigma yield stress divided by 2. I will get this plot, and then I have the ultimate stress here and then the yield stress here. So this is just the indicator for the uniaxial tensile tension test. Okay, let's see if I have the same for the triaxial stresses. This is for the triaxial stresses, just like here, but this is more onto inner, or you take one part element. So the triaxial will show the direction towards the structure, where the sigma 1 almost equivalent to the sigma 2, and then almost equivalent to the sigma 3 and sigma max. Okay, let's take a look at this example. Given the following choppy V-notch impact specimen results for the ABS B steel, so you plot an appropriate curve of K1D and K1C versus temperature. Assume the steel has a static yield strength of 40 ksi and a dynamic yield strength of 65 ksi. So they give you some other information on how much is the temperature, and then how much is the energy for each temperature. So you need just to plot this in a graph like this one. Temperature and the yield stress. This one. No, this one. Okay, once you plot that, you can just try to do the test in using Excel or so on. So you can see the trend there. Okay, the next topic we cover about the fracture mechanics design. We'll see if you have any other question. The same, you can raise that in the online session. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.